Okay, so let's start. So remember that yesterday we were discussing polynomial identity testing, and we saw a randomized algorithm for a univariate polynomial, that is a polynomial with just one variable. Okay, and to prove its success probability, we crucially use the fact that polynomial in just one variable of degree d has at most d many roots, right?
Yes.
Yeah, but then we saw that even like polynomials of degree 1, for example, x minus y in more than one variables can have infinitely many roots, right? For example, the entire line x equals to y is the zero of this polynomial, right?
Yes.
Yeah. So now what we'll do is today uh, we'll give a randomized polynomial time algorithm for PIT for general multivariate polynomials. But even before that, let us just handle this simple case where the polynomial is linear. That is, uh, all monomials in it have degree 1. So it looks something like a1 x1 plus an xn plus b. Okay, so the polynomial x minus y is of this form, right? So even polynomials of this form can have infinitely many roots. And so what we did yesterday might not directly apply, right? Because, yeah, the roots are infinite. Let's see how we can handle this case. And then we'll combine the idea from what we did yesterday and what we do here to give a general algorithm. Okay. So again, the algorithm is just the same thing. Uh, how did I write it? Okay, I fixed S first. Okay, in this case, I can just get away with 0, 1. Mm, okay, like this. For all I in pick AI uniformly at random from S. Yeah, so the algorithm is very similar to what we did yesterday. So we would pick a random, so we would pick okay, so yesterday there was just one variable and we picked a random value for it, right? Today we have n variables and we are going to pick random values for all of those n variables and then evaluate the polynomial at the random values. If it's zero, we'll say that the polynomial is zero, and if it's not zero, we'll say that the polynomial is non-zero. Okay. So is the algorithm fine?
Yes. And
Yeah.
yes. Yes. Yeah.
So now let's look at the runtime.
And
So
from where are we picking the values of these coefficients, say AIs?
from the set S, where S is a 0, 1 over here.
Okay. So why only 0 and 1 and not any other value?
Okay, so in fact, any two numbers would have worked over here. So let's say A comma B, where A and B in Q would have worked.
Okay.
So that was happening even yesterday, right? So I picked S to be 1 to 2D, but
Yes.
any set of size 2D would have worked because any set of size 2D would have at most D roots, right?
That is true. That is true. But then picking the values from 1 to 2D is, I mean,
Mm.
makes sense. But then picking the values either as 0 or 1, I mean, does not make sense. Why so? Because quite possible that the value of AI could be half and the value of, I mean, AI plus 1 could be 3 by 4. Quite possible. Then why to pick values, I mean, either as 0 or 1 only?
Okay, so AIs are the okay. AIs are not the coefficients. AIs are the values that I pick.
I could
Okay, so
not get.
let me write it like this.
Yeah.
Okay, so F, so my C1 to Cn are just the random values that I pick, right? They are not the coefficients of the polynomial. The polynomial is this. So I think this was causing the confusion. I wrote an as the coefficients and then used an as random values. So what I'm doing is this. If my coefficients are a1 to an, I am picking Ci's and plugging Ci's over here.
Mm-hmm.
So what was your question there now?
Yes, so my question is that actually this, I mean, both the lines of this algorithm are not making sense. That so basically we are picking the values of the coefficients of the CIs from the set
No,
of.
Ci's are not the coefficients. Okay, so the polynomial f, okay, f looks like f of x1 to xn looks like a1 x1. Okay, so this is what f looks like. Okay, so these, uh, these are the coefficients.
Yeah, these are the coefficients. Yeah, all right, all
Right.
right.
Now, what am I doing? I'm picking C1 to Cn.
Okay,
And where am I plugging in C1 to Cn in this formula?
so you are picking the values of C1 to Cn, say from the set S. Actually, that is not making
Yeah.
sense.
Okay, forget about S. Let's say I have some Ci, C1 to Cn. Now, in
Yes.
this formula, where would C1 to Cn go? When I write f of C1 to Cn, where does
Mhm.
C1 to Cn, where do C1 to Cn appear in this formula?
Yes, so it would be like A1 C1 plus A2 C2 and then
Right.
so on till A and Cn.
Okay. Plus B. Right. Okay, so now why does it not make sense to pick C1 to Cn from 0, 1?
Okay, so it does not make sense. Why so? Because what could be the meaning of this thing that we are eliminating some of the, I mean, excise from the equation from the polynomial.
Okay, what
Uh,
does elimination mean?
so that so if we if so it means that I'm only considering the coefficients of x1 but not considering the coefficients of x2 and considering the coefficient of x3 and not of x4. So why so?
Okay. Okay, so let me go back to what we did yesterday. Yesterday, my set was 1 to 2D, right?
Yes, so in this case we were selecting one
Okay,
value
so
uniformly
what
at
would
random.
happen if my set were 1 to 2D minus 1? Would the algorithm still have worked?
Uh, what did you say? So
So
I could not get.
instead of S being 1 to 2D, S was
Yes.
0 to 2D minus 1.
So had this been 0 to 2D minus 1 is fine because ultimately I'm picking one value uniformly at random from the 2D number of the possibilities, and out of those 2D
Right.
number of the possibilities, D will be
And
right.
any set of size 2D would have, right.
Yes.
Over here, including 0 in the set is fine, right?
So including here is 0 is fine, no issues. Yeah.
In fact, any set of size 2D would have worked.
Yes. Yes.
Okay. So now my question is why over here bother you uh, in the like current algorithm? So suppose I were to replace 0, 1 by 1, comma 2. Would this be fine?
In fact, this is also not fine because we have been given how many variables? We have been given n number of the variables. So if we
Right.
have been given n number of the variables, then why to pick values of these variables from a set and which has got only two elements? Why not a set having more than say 10 elements or say 2n number of the elements?
Okay. So yesterday I used 2D. for some reason, right? So today, the say, okay, the size of set being 2 would be become clear when we look at error probability.
So my point is that there we consider the univariate thing, and
Right.
so at moreover we consider that the degree is equal to d. So therefore the number of roots would
Hmm.
be less than or equals to d. So probably the reason of
Okay.
select d was that out of 2d number of the possibilities, d will make
Hmm.
sense, not make sense. So now here we have n number
Okay.
of the variables given. So what is the degree of this polynomial? So does this mean that the degree of this polynomial is one
What is the degree?
or
Okay, what's the degree of this polynomial?
yes? So okay, so the degree of this polynomial is one.
Yeah,
Is
and
this the
what's
reason?
2 times 1?
Oh,
Not
you mean
exactly.
oh
Not
yes, yes,
exactly. Okay, so no. Okay, so the reason is not exactly that because you see over here, I could pick 2D because I knew that the number of roots are going to be at most D, right?
yes, yes,
Over here, I have no such guarantee. So let's suppose all of these were 1 and this was 0. Then I have too many roots, right?
I have too
So
many.
let's just say x1 minus x2 was my polynomial. So a1 is 1, a2 is minus 1, everything else is 0.
Okay, okay, okay.
Now even this polynomial has many roots, right? Infinitely many roots.
Yes, yes, true, true, true.
Yeah, so the reason is not that okay, I will have just one root. That's why I'm picking this. But yeah, the reason does have something to do with the degree. That won't become clear here, but it would become clear when I look at the next, like look at a general algorithm. So over here, I would give a very simple reason why 2 works. Okay,
Yes, yes.
okay. So yeah, so the reason for 2 would become more clear when we look at the error probability. But right now, let's look at the running time. So what's the running time?
So running time here is of the order of n.
Yes, because I'm picking n random values and picking one random value takes costs me like just one random coin, right?
Yes.
Okay. Now let's look at the error probability. So what do I want? I want to find, okay, first of all, uh, case one. So when f is identically zero, what would be the output of the algorithm?
So if f is the is equal to zero, so if it is zero, then the output would be zero.
Right. If it's zero, the output will always be zero. So when f is equal to one, okay, so now let's look at the case where f is not zero, right? So I am interested in this probability, and this is just the same as yeah. So this was just simple like algebra, right? Nothing is deep going on over here. Now let's perform this thought experiment. Suppose that, okay, I should have written Cn over here because that would work much better with the experiment I have in mind. So let me write it like this. Okay. Okay. So we are interested in this probability, which is the same as this. And over here, all I've done is moved some things to the RHS, right? Okay. And I've also picked AI. So what is AI? AI is the last value of, so AI is the largest number in 1 to n. The AI is non-zero. Is the choice of AI,
Yes.
yeah, okay. And there is, and it's possible that no such AI exists, right?
Yes. Yes. So when f is not
Yeah,
equals to 0, uh, but when f indeed is
yeah,
not equal to 0, then we are trying to find that what could be the possibility that this expression comes out to be a 0. Is it like this?
right. Yes. Okay. So okay, there are two cases. One, some AI is non-zero. Another, all AIs are zero, right? But if all AIs are zero, we know that F is non-zero, so B has to be non-zero, right? But in that case, F is a constant, right? So no matter what I plug in place of x1 to xn, the, the evaluation of F is always going to be B, which is non-zero, right?
Yes, yes, right, right.
So the algorithm would always output non-zero.
So yeah, algorithm will output non-zero if under the condition that all the AIs are equals to 0.
Yes. Okay.
But then that would be a very, very specific case wherein the given polynomial is just a constant and nothing else.
Yeah. But okay, so the only reason I wrote this was to handle this one case.
Okay.
Because the more interesting case is this one.
Yes, yes.
Yeah. Okay. So now AI is non-zero. So what I can do is I can write 1 over AI, right? This makes sense.
Yes, AI cannot be 0 because of the given equation. AI is in the denominator.
Yeah. Okay. Now let's perform this thought experiment. So I is the last number. Ah, I is the last number such that AI is zero, right? So now over here, let us suppose that I first pick C1, then C2, then C3, and so on, right?
Uh, I could not understand this. Can you repeat?
Okay. So I'm picking this in order, right? So I first sample C1, then I sample C2, then I sample C3, and so on.
Yes.
So now let me stop after sampling Ci minus 1, but before I sample Ci.
Okay.
At that point, this value is fixed, right?
Right. Right.
Okay, so now let's say this value is gamma.
Okay.
Then the only possible, then f of C1 to Cn is 0 if and only if Ci equals gamma, right?
Yes.
But what is the probability of Ci being gamma? At most half, right? Because either gamma is outside 0, 1, in which case Ci would never be gamma, or gamma is 0 or gamma is 1, in which case the probability of Ci being gamma is half, right?
Yes. Yes.
So the probability of Ci being gamma, and therefore f of C1 to Cn being 0 is at most half,
Yes.
right? So is this fine?
This is fine because the degree of the polynomial is 1. So it looks slightly strange, but still the probability would be half based on the, I mean, the previous argument wherein last yesterday also we saw that the
Hmm.
probability of, I mean, not 0 was less than half.
Yeah,
So based on that, yeah, makes sense. Yes.
yeah. So over here, what we used was that there is only, okay, so once I fix everything other than Ci, there's only one value for which, one bad value of Ci. And yeah, so I can use just two values, right? Now, let me just do what I wrote, said more formally. Okay, let me write it from here. This is going to be a long expression. Okay, so I said it, okay, let's fix everything other than Ci and see what happens, right? But the formal way to do that is this. Probability. Yeah, okay, so the formal way to fix something is to condition on that and then multiply with the probability. Because what I'm saying here, I'm saying that this is true and I fix C1 to Ci minus 1, right?
Yes. And what about this summation thing? Is this, I mean, only
All
for the,
values of Ci to Ci minus 1.
so is this summation continuous till the second probability, or I mean,
Okay, oh, okay.
only
This is
for
the
the
entire
first?
thing.
Yes. Yes. Yes.
Yeah. So all I'm saying is, okay, I argue that for one value of Ci to C1 to Ci minus 1, there is only one bad value of Ci. But there are many values that C1 to Ci minus 1 can take. Fine. So condition on every one of them and sum over all the probabilities, right?
Yes.
That
Yes.
so this is a formal way of saying that okay, I have fixed something. Okay, so
Right.
now we saw that this is going to be at most half, right? And this is half because I can take this half out common, and this sum is just one, right? Because I'm saying I'm summing over all the values of Ci to Ci, C1 to Ci minus 1 and saying, asking what's the probability that this is the value that they take. So when once I sum, that becomes one, right?
Yes. Yes.
Yeah. Okay, so this is at most half. So is this fine?
Yes. Yes. This is fine.
Yeah. Okay, and what type of algorithm is this?
So yeah, this is clearly Monte Carlo.
Yeah, again, single-sided Monte Carlo, one-sided error Monte Carlo, right?
Yes. Or it could be QRP kind of thing.
Yeah, so this isn't co-RP, but so over here we are, so it's one-sided error, right? Both RP and co-RP are one-sided error.
Yes. Yes. Yes.
Yeah. So this is fine, right?
Yes, yes.
Okay, so in these two special cases, we saw two ideas. So in the first case, we used the fact that the degree of a univariate polynomial in D, univariate polynomial of degree D has at most D roots. So that's the first idea we used. The second idea we used was, okay, we can fix or condition on the values that that some of the other variables take and then argue, right? So two ideas. Uh, I bound on the degree gives me a bound on the number of roots and I can condition, right?
Yes. So can you repeat what you said just now? This seems to be an important statement. Actually, because of the audio issue in the Teams, so
Hmm.
whenever you speak fast, so actually that becomes not understandable. This is because
Okay.
of this time. Because if you conduct this meeting on the Google Meet, then your
Hmm.
audio is crystal clear. Whereas in the Teams, I hear that as if you are speaking from within an empty room. So probably you are sitting in an empty room, so that voice, I mean, echoes actually. And when you speak something fast,
Okay.
so that actually create lots of hindrance, and I cannot understand what you said.
Okay. Okay. So because I can try to speak slowly.
Yes,
Okay.
thanks for that.
So yeah. So we saw two ideas. So yesterday we saw that for a univariate polynomial, if it has degree d, I can upper bound the number of its roots by d, right?
Yes,
And today we saw that if I have multiple variables, I can fix the values of all the variables except one variable and then argue.
yes,
So now we would combine both these ideas for the general case. Because in the general case, there would be multiple variables and the degree would be more than one, right?
yes,
Okay. And okay, so for the general case, the statement is called the Schwarzschild lemma, and it states that let f be a polynomial over rationals in n variables, which is non-zero, and let the degree of it be d, at most d, right? And let S be any subset of Q. Then, okay, again, AIs might create confusion because sometimes I use them for coefficients. So let me say, let me just use C1 to C. Yeah, then when I pick C1 to Cn uniformly at random from S, the probability that f of C1 to Cn is zero is at most d over size of S. Okay, so is the
okay.
statement fine?
Uh, yes, yes, it is fine, except that we are dividing I mean, in the denominator, we have the cardinality of the set of the rationals, and the set
Hmm.
of the rationals, I think, would be infinite.
Wait, why would it be infinite?
So, what is the cardinality of the set of the rationals? The set of the, I mean, all
Okay, okay,
rationals.
S is not rational, right? S is a subset of rationals. It is any subset of rationals.
Oh, I see. Yes, yes.
Pick a subset of rationals, plug that over here, that gives you a value, right?
But then this subset of the rationals could be pretty long, pretty large. Its cardinality could be
Yeah,
very high.
so the larger this is, the smaller the bad probability.
Okay, okay.
Yeah, and that happened in the case of univariates as well, right?
What happens in the case of?
So even in the case of univariates, so let's say if instead of 1 to 2D, I had picked 1 to 1000D, then this probability would have been 1 over 1000, right?
Yes, 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 yes. Right.
Yeah, so even over here, it was 1 over size of S. And even over here, if I instead of 101, I had picked 0 to 1000 or 0 to 999, so 1000 values. Again, I would have gotten 1000 over here in the denominator, right?
Yes, 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 correct.
So, like size of S is always there. It's just that I haven't explicitly stated it in one and two.
Right, I understood this. Yeah.
Okay, yeah. Yeah, so we'll prove this by induction of the number of variables. Okay. And the number of variables is 1. In this case, we already saw, right? In this case, it's a univariate, and uh, okay, now there is just C1 because univariate. Yeah, so this was the first thing that we saw to this time, right?
Yes.
Okay, so now in the induction step, assume that
So I would like to stop here that so we have
yeah,
seen that this probability is less than or equals to d divided by delta, and delta was equals to 2d, and because of this,
right,
okay, okay, yes, that's right.
right. Okay, so in the induction step, our induction hypothesis is going to be these. Assume that yeah. So assume that the lemma is true for all non-zero polynomials in at most n minus one variables. Okay. So what does that mean? If I have a non-zero polynomial g in at most n minus one variables, and its degree is d prime, then the probability that this would be zero would be d prime over size of this. So is the induction hypothesis clear?
Yes, yes.
Okay. So now, uh, okay. So now what am I doing? I am writing f x1 to xn as a polynomial in just xn, but now the coefficients are coming, coefficients are themselves polynomial in x1 to xn minus 1, right? This I can do.
So what this f naught here is?
Some polynomial of degree 0, sorry, uh, okay, I'll get to the degree later. So this is some polynomial in x1 to xn minus 1. So the way I would obtain this is the following. I would look at all the monomials in x1 to x, f of x1 to xn that do not contain xn. Okay,
Okay, okay,
so this would be the sum of all those monomials.
okay,
Similarly, I would look at all the monomials in f of x1 to xn which contain xn. So the degree of xn in that monomial is 1, right?
mm-hmm.
So
Mm-hmm.
it looks something like x1 squared, x3 cube, so on up to xn. So xn appears with the degree 1. So I look at all of those monomials, take xn common from them. Whatever remains, that sum is f of x1 to f1 of x1 to xn minus 1. Okay.
So you are using the term sum. So what this sum here refers to what? The sum of the
Addition.
monomials excluding the term
Yeah, yeah.
x.
Okay. So let's say I had x1 squared, x2, xn. So I would take xn common from both. Then whatever remains, that is my f1. So it's this plus this.
Oh, yes. Yes.
Yeah. Similarly for f2 and so on up to, okay, I'm using I furtherly. Yeah. I can write this all the way up to xi where I is less than b, right? The degree of the polynomial is at most b. So the degree of the individual degree of xn can be at most b, right?
Yes.
So I've written f like this. Now, okay. Yeah, you were asking something?
No, no, I was not.
I
I
was-
was.
Okay, okay. Okay, so now, uh, suppose that, okay, let's perform that experiment again. So let's say I picked values for x1 to xn minus 1, and these are c1 to cn minus 1, right? So the
Yes.
moment I fix the values of c1 to cn minus 1, all these become numbers. Right.
Right. Right.
So then what do I have? I have f of c1 to cn minus 1 comma xn, right? And this is the univariate polynomial in xn of degree I.
Right. Right. So from the multivariate, it has converted. It has got converted into the univariate.
Right. By fixing some values, i.e. by conditioning.
Yes. Yes. Yes.
So is this fine?
Yes. Yes. It is fine.
Yeah. So we have used the first idea conditioning. Okay. So using that, we have obtained a univariate of degree at most I, of degree I, which is at most b, right?
Yes. Yes.
So now, when I pick a random value for xn, this polynomial would be non-zero with okay would be zero with probability at most one over size sorry I over size of s, right?
I could not hear this.
So now this thing is a univariate in xn.
Yes. This is correct.
So and the degree is I, which is at most b,
Yes. Yes.
right? So if I were to pick a random value for xn, then my polynomial would be non-zero with probability would be zero with probability at most I over size of s, which is at most d over size of s, right?
Yes, so it would be I of the size of S, and since I less than or equals to D, so D by the S. Yes, it is correct. It is correct.
Okay, there is one issue with this argument. Can you tell me what that issue is?
Uh, okay, so
Okay, so I have a univariate. Okay, so let me tell you this. Okay, so I have a univariate. That is fine. The issue was in the argument after getting a univariate.
so yeah, but yes. So and we are picking these values of x1 to xn minus 1 from this set, from the set S.
Yes, right?
Uh, okay, so that value would be less than or equals to D by S, making sense from the first observation. It is making sense. So yeah, but the thing is that we are selecting xn thing randomly. So xn could be anything. So it could
Hmm.
be it could be x1 also. It could be x2 also.
Yeah,
right? So if that is the
Right.
case, so then I'll have to take the sum of over all the exercise things. Like say the probability. Last time we saw the probability that okay, this value is equal to zero with the probability of less than or equals to half. So
Hmm.
wherein we were actually having a univariate thing. But there also we are actually having an univariate thing only. So that argument is not valid. Yes, I understood. So yeah, I could not identify any flaw in this. This argument
No,
seems
no, okay. So over here, that's not the issue. The issue is this. So I was picking random values for xn minus 1, right? These were C1 to Cn minus 1.
yes,
But what if at C1 to Cn minus 1, this is 0, this is 0, this is 0, this is 0, everything is 0.
yes,
F of C1 to Cn would still be 0, right?
yes,
So the argument I was making that, okay, once I've picked these values, this would be non-zero, probably d over size of s, only works if all of these, at least one of these is non-zero, right?
yes, yes.
Yeah. So that was the issue with the argument. And now I'll like show you how to fix that issue. Okay.
But then, where is this thing an issue? Because I mean, in the first observation also we saw that if the value of the polynomial is equal to zero, if the value of the univariate polynomial is equal to zero, then we will get then its probability of becoming a
Right.
zero was
Okay.
one. Then its probability of becoming a zero was one. And here also, is this a flaw that there the probability of becoming the entire polynomial
No,
is
no, no,
equal
no.
to
So over there, here my multivariate is non-zero. When I'm plugging in values for x1 to xn minus 1, it becomes a zero univariate, right? So it goes from non-zero to zero.
yes, yes,
And that's an issue, right? So in the
yes,
univariate case, that won't happen because I'm not doing anything. My polynomial is univariate to begin with, right?
yes.
Yeah. Over here, I had a multivariate polynomial, which I converted to univariate. And in that process, I messed up. I got zero.
Mhm, mhm.
Yeah. So now let's see how to fix this. So, okay. I'm not writing where what this probability is over. It's over C1 to the random just C1 to Cn. Okay. So now let's just focus on one this for one some value of C1 to Cn, right? So my claim is this. This is less than or equals to. Okay, let me write from here. This is going to be long discussion. Okay, let me do it like this. Okay, let me write it. Let me add one more step. Okay, so what am I? I'm just looking. I'm just looking at one of these. And what am I doing? So I am dividing this event into two parts. Okay, so over here the conditioning is there. I'm sort of ignoring it. So let me just write it. Okay, let me not, because in the next step I don't want to write the conditioning. So let me say I'm ignoring conditioning. Rather suppressing. Okay, so I have this event. I'm like there is a conditioning over here. I'm just not writing it. But this event can be split into two distinct events, right? The polynomial, the evaluation is zero, and the polynomial, the univariate in Xn, which I get after putting E1 to Cn minus 1 is also zero, plus the probability that the evaluation is zero, but the univariate is non-zero, right? So is this fine?
Yes.
Yeah. Okay. And now the first probability can be further simplified, because if the univariate is itself zero, then all of its evaluations are going to be zero, right? The first probability is just f of okay, is this fine? Why I can write this? Oh, sorry, this should be Cn.
So, I mean, how did you reach to this conclusion?
Okay, okay. Sorry, not Cn. Xn. Yeah, okay. So if f of x, this is zero, then this is always going to be zero, right?
Yes.
Yeah, so this implies this, so I can just replace this by this. Because whenever this happens, this would always happen. So A intersection B just becomes B,
Mhm.
because A is a larger.
Yes.
Okay, so that's the first part. And what about the second part? I can write the second part like this, right?
Yes.
Okay, so now, okay, okay, let me do one more step, then I can go to simplification. Plus. Okay, so why can I write this? So all I've done is I've removed this probability. So okay, I know that this is the probability, right? So this is going to be between 0 and 1.
Yes.
So what I've done is I've upper bounded this by 1.
Yes. Yes. Yes.
Yeah, this can only increase the number, right? Because this is always going to be less than or equals to 1. So this would be like, let's say 0.99. When I make
Yes.
it 1, that only decreases, right? Sorry, this value can only increase.
Yes.
Okay. So now I will write it like this. Sorry, J. This I'll copy. Okay, so now then comma x and b 0. So when would the univariate be 0? Let's go to the univariate. This would become 0 when this becomes 0, this becomes 0, this becomes 0, and this becomes 0, right? So when all the coefficients of xn become 0, right?
Yes.
And over here, what I'm saying is there exists some coefficient of x, which xn, which is non-zero. Oh, wait, okay. No, 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 this. Okay, so for all j, I want 0, right? So for all j, this is 0. Yeah, this was the complement probability. So the polynomial becomes 0 when only for all j, the coefficient becomes 0, the corresponding coefficient becomes 0, right?
Yes. It is. It is right now.
Yeah. Okay, so now I can write it like I of yeah, this I can write, right?
Yes.
Okay. So now I am picking C1 to Cn minus 1 uniformly at random, right?
Yes.
And if you go and look at Fi, so what's the degree of Fi? So the total degree is D, and the degree of Xi is Xn is I. So this degree can be at most D minus 3, right?
Right.
Right. So I have a polynomial in n minus 1 variables of degree at D minus I, and I'm saying that it becomes 0. The polynomial is non-zero, but it becomes 0 after this substitution. What is this?
So it is becoming zero because of the substitution. Why so? Because we have because we put the values of the C1 to Cn minus 1 in such a way so that f of C1 to Cn minus 1 becomes 0, and then we are multiplying this entire thing by, say, xn. So since
No,
f
no,
of
no, no,
C1
no,
is
no, no.
0,
That's not happening. So what I'm okay. So I'm interested in
I
this
mean, how
probability,
did
right?
you reach to this line? I mean, prior
So
to
from here
this
to here,
and from two steps above, wherein you first time you use less than or equals to.
here.
So wherein, I mean,
Okay, so you want
at the location where
okay.
the first time, yeah, first time you use less than or
So you
equals to,
want me
we
to
have,
ex okay. So do you want me to explain how I went from here to here or from here to here?
no, from here, wherein you use this less than or equals to first time, you can you
Okay,
put your
from
marker
here,
here? Yes,
right?
from here to the next line. Uh,
Okay, okay. So I am saying that over here, f of c1 to cn minus 1 comma xn is 0. That is, once I place in C1 to Cn minus 1, I get a univariate in Xn, right?
Yes.
I am saying that univariate is 0.
So that value is
And
0. Why? Because only the value of
no,
xn is
no,
being.
okay, no, that value is not 0. So this statement, what does this statement mean? This statement means, all I'm saying is, this statement means that the univariate is 0, right?
Univariate is 0. Right, right.
There is a probability sitting outside. So I'm not saying this is 0. All I'm asking is, what is the probability of this becoming 0, right? So this has not become 0. All I'm saying is, okay, with what chance can this become 0? That's what I'm
Yes,
interested in, right?
yes.
So is this fine?
Yes, this is.
Okay. But I'm interested in the chance that the univariate becomes 0. Okay.
Yes, yes,
I'm asking
yes.
the question, when can the univariate become 0? The univariate becomes 0 when all of these polynomials evaluated at C1 to Cn minus 1 becomes 0, right?
Yes, yes,
Okay. And that is exactly what I've written over here.
yes.
Okay. Now, let's see how I went from here to here. Over here, I have I plus 1 many events, and I'm taking their intersection, right? Because for all means intersection.
Yes.
And all I'm doing over here is, okay, wait, this should be an equality, sorry. Uh, yes, this is an equality, this is an inequality. Okay, so over here, I have an intersection of I plus 1 many events. Let me call these events E1, E0 to EI. Okay,
Mhm.
so over here, I'm interested in the probability. But the probability of intersection of all these events is less than or equals to the probability of just one event happening, right?
Right, right. And
Right.
why so?
Now,
Why so? Uh,
okay, so, okay, what do I mean when I say that E1 intersection E2 happened? E1 happened and E2 happened, right?
yes,
But when E1 happened and E2 happened, E1 happened, right?
right, right, right.
Yeah. Okay. And now, okay, so now over here, I added this. Can you tell me why this makes sense? Why should one of these be non-zero?
So one of these should be non-zero. Then only I'll
Can you hear
get,
me?
because one of them should be non-zero. Then only I will get some xn term. Otherwise, from where will I get this xn term?
Oh, okay, no, so the polynomial need not have x in, right? The polynomial can just look like, so this makes sense because, okay, what was my assumption? My assumption was f is non-zero. I've written that over here.
Yes,
So when I write f like this, if all of these are zero to begin with, then f is a zero polynomial, right? Which is a contradiction.
yes, yes.
So at least one of the coefficients must be zero. No,
One.
sorry, must be non-zero,
Yes,
right? Okay. And what am I doing is, I am saying, okay, the largest one that is non-zero is fi. Multiple of them can be non-zero. The largest one that is non-zero is fi. That is how I have defined fi.
I could not hear this. You said just
Okay.
now.
Yeah. So, okay, so I know that multiple of these coefficients must be non-zero, right?
Yes, yes.
I'm saying take the largest one that is non-zero.
Mhm.
That is fi, and then over here I would have xn to the I. And after this, everything would be zero, right?
Yes, yes.
Yeah. So that's how I picked fi. Okay, so now let's go to here. Over here, what do I have? Fi, which is a non-zero polynomial,
Mhm.
evaluated at random values becomes zero.
Mhm.
This is a non-zero polynomial in
Mhm.
n minus 1 variables. Okay.
Mhm.
So by the induction hypothesis, the first part is at most right.
Yes, yes.
And what about the second part? So over here, the univariate is non-zero.
Mhm.
But when I plug in Cn, the polynomial becomes zero.
Mhm.
So this must be at most I over size of S because the degree of the univariate is I, right?
Yes, yes. Right.
Yeah. Okay, so now, okay, so here to here makes sense, right? So over here, I use the induction hypothesis. Here, I use the very first observation that a univariate has at most I roots, right?
Mhm.
Okay. So now the question is what is the degree of Fi?
Right.
Let me go here. The degree of this entire thing is at most D.
Mhm.
This is I. So this can be at most D minus I, right?
Yes.
So, okay, because induction hypothesis. So is this type? Yeah, so this proves the lemma, right?
Yes. Yes.
Okay, so now that we have the lemma, the algorithm is simple, right? We'll just do the same thing. The algorithm is very simple. What's its running time?
Yes. So
There are n variables, so I'm picking n random values. So there is order n is already there.
yes.
Times log d because to pick, so I'm choosing from this set. It has 2D many elements. So to pick a random element from here, I would need log 2D many random coins, right?
Yes. Yes.
Yeah, so that's why you get this extra log factor. Okay, so now what's the error probability? Again, when right, and when f is not equals to 0, I can use the Schwarzschild lemma, right?
Yes. Yes.
Hmm. The algorithm outputs 0 if and only if at a random point the polynomial most d over size of s. Size of s over here is 2d, right? Yeah, so
Mhm.
is this fine?
Yes, yes.
Yeah, and again, this is a single-sided, uh, like one-sided error Monte Carlo, right?
Yes.
Yeah, so this was all that we had for polynomial identity testing. So if you have some questions about this, you can ask now. Is now we'll start looking at the applications of this.
Yes, so I found this proof quite interesting, but then it requires some
Right.
time to understand the proof because I think this proof is
Yeah.
lengthy. It requires, I mean, so need to think at
So like,
multiple.
yeah, so I think once you look at this proof a few times, it starts becoming intuitive. But yeah, for example, I think when I first looked at it, we, okay, yeah. So when I first looked at it, I think it was yeah, it was these two transitions that always gave me trouble for the first few times.
Okay, okay. So I will look
Yeah,
these conditions a few more times. But then
yeah.
can
Okay.
you
No, like for every person, this would be different.
yeah,
Like,
okay, okay, okay.
yeah,
So can you summarize the important, I mean, the result of this theorem from a layman's perspective, that if we are
okay.
randomly assigning, say, if we are randomly picking a string, if we are okay, and then how this lemma or how this theorem affects uh, the the polynomial identity testing.
Okay, so this lemma is sometimes also called the is also called the polynomial identity testing lemma. So this lemma is itself the identity test, right?
Okay, okay. I
Yeah.
was
So
under
for this lemma,
I was
yeah,
under the
because
impression that if you want to show that px is equal to qx, if you want to show the equality of the two polynomials,
correct.
so then we go for the polynomial identity test.
Okay. So okay, the problem polynomial identity testing has two definitions. One is given two polynomials, they are the same or they are different. So decide whether they are equal or they are not equal.
Yes.
Another definition is the one I have used over here. Given a polynomial p, decide whether it's zero or not.
Okay.
But you see, the first definition reduces the second definition because, okay, what do I want to check? P equals Q, right? But
Yeah.
then look at P minus Q. If
Mhm.
P and Q are the same, P minus Q would be zero. And if P and Q are different, P minus Q would be non-zero, right?
Yes.
So to solve the first problem, all I need to do is check that the polynomial G defined as P minus Q is non-zero.
Right.
Yeah. And like, so I use this definition. And another reason I use this definition is like, it's simpler. There's just one polynomial you have to worry about.
Mhm.
Yeah. So there are these two definitions that they are equivalent.
Mhm.
Yeah. But yeah, at a lot of places, the first definition is used. That I agree with.
Yes.
Yeah. So is this fine?
Yes. Yes. Yes.
Yeah. So in the layman's term, what this would say with respect to the first definition is, okay, you have f and g. You want to check they are the same or they are different. All you have to do is look at f minus g and apply this lemma to f minus g.
Mhm. Mhm.
Yeah. That is what this lemma is saying for in layman's term to the for the first definition of PIT.
Right.
Yeah. Okay. So now, if there are no other questions, we can start looking at the applications. Okay. So the first one is called the Frival's algorithm, and it's for the following problem. I give you three matrices A, B, and C. So I also briefly mentioned this yesterday. So I have three matrices A, B, and C, and I want to check if AB equals C. Okay, so is the problem clear?
Yes.
Okay, so now what is the naive algorithm for this?
Okay, so first I will check the dimensions of the A and B, whether the dimensions of
Hmm.
B are
Okay, so all of them are the same. For simplicity, all of them are the same.
oh, n into n, right?
Yeah, yeah. No, let's not get into dimensions. Let's just keep it simple.
Okay, okay.
Yeah,
So yes. So then to check whether I mean this C is equal to AB or not. So yeah, I will keep on. So I'll use the traditional way of multiplying the matrices, say
right.
in the effort of the order of NQ. And
Yeah,
most I can do one thing, that instead of computing the entire product, I will keep on comparing that whether the value of the first product of the first row and the first column, whatever I get, is same as the value of the C that entry in the C matrix or not.
right.
So that I can do.
Yeah, but in the worst case, the last entry would be different, right? Everything else would be the same.
Yes, yes.
The run. So what's the runtime of this? Order n to the omega, where omega is equal to the matrix multiplication coefficient. Okay, so what does omega represent? Well, so we know this trivial algorithm of order n cube for multiplying two matrices, right?
Yes.
But then there is Strasson's algorithm as well,
Yes.
which does n to the 2.83. And like there are many better algorithms. So I think right now the current best is n to the 2.37.
Yes. Yes.
But there is no guarantee that this is the best, right? That you cannot do better than n to the 2.37. So people have defined this constant omega, which says, okay, the best possible algorithm is n to the omega. We don't know it yet, but it exists, right? The best algorithm exists. We just haven't found it yet.
So do we have any lower bound analysis of this, that
Yeah, n square. You can
howsoever
never
hard we try?
go below n square, right?
Ah,
Because there are n square many outputs. You have to output all of them, right?
yes, yes, yes.
Yeah. So right now we know that 2 less than equals to omega less than equals to 2.37.
Right, but even this equality in the left-hand side, I mean, does not, I mean, seems to follow the common sense, because if W becomes equals to 2, so then the
Hmm.
addition of the matrices would be same as the multiplication of the matrices, and that is very
Yeah.
much intuitive.
Okay. So some people conjecture that omega is 2. Some people believe it's not 2. Strassen doesn't believe it's 2. So yeah, the jury is out.
Okay, okay,
Yeah. Yeah. I don't know what I believe. I don't think I have very strong opinions about omega.
okay, okay.
Yeah. Okay. But right now, okay. So as of now, this naive algorithm would take n to the 2.37 time. Okay.
Yes, yes.
Okay. So now I have a paragraph about where this problem arises. But I briefly went over this yesterday, right? That if you want model ML model to a cloud, most of the computations are matrix products. So yeah, if you want to verify that the cloud did it correctly, you have A, you have B, you have C. Sorry, you have A, you have B. The cloud service provider gives you C, and you want to check this. Okay, so I won't go over this again.
Mhm.
Yeah, so okay, so now that we have seen a naive deterministic algorithm, let's see a better randomized algorithm. And the randomized algorithm would take order n square time. Now, first of all, you cannot do better than order n square, right? Because there are at least n square entries in A, B, and C, and you have to at least check, at least intuitively, you have to check that these all are the same, right?
Yes, yes.
Yeah. So let's see an order n square algorithm. Okay. So it does the following. I will worry about the analysis. Let me fix an S. Multi-linear. This would fine. Okay, 0, 1, 1, 1 suffice. Because the degree would become 2. So let me have it from 1 to 4. Okay, this is going to be n 1 cross n. So I don't need to work. Wait. This is n cross n. I am multiplying it with 1 cross a vector of. So this is 1 cross n. And what's B2? B2 is also 1 cross n. Yeah, so I can say actually I should do. Wait. So R, let me do it. Okay, so this is the algorithm. So what we are doing is uh, we are picking two random vectors. Let's think of these as column vectors. Okay. And computing the product of A transpose and R1 and B and R2 and checking computing this A B1 transpose B2. So what is A? It's R1 transpose A B R2, right?
Yes, yes,
And we are also computing R1 transpose C R2.
yes,
So if C and AB were the same, these would be the same, right?
yes, yes,
Right. But now what we are supposed to show is that if C and AB are different, these two would be different. Okay.
yes.
Yeah. So what is the running time of this algorithm? What am I computing? And this, and this.
Yes, so yeah. So basically, we are checking that whether this, I mean, this would require calculations. I mean, getting the values of the V1 and V2. So basically, we are comparing two expressions, and
Okay. Yeah.
so
Okay. So yeah. So, okay. That is happening over here. But even before that, what is the cost of computing V1 and V2?
So cost of the computing is, so basically here also, while computing the V1, we are multiplying two matrices only. We are multiplying A matrix and with a vector.
So order n square time, right?
At least it could be higher also.
I,
Why?
no, it can't be higher, right? Because over here, this is a vector. So it's n cross n multiplied by n cross 1,
Yes, so that would be n square.
right?
Yes, yes. So
Yeah, same for V2, right?
yes, and then to compute A1, then to compute A, and so V1 is a matrix of the dimension n cross 1, and this would also be n cross 1. So again of the order of n square.
It's n cross 1, n cross 1. So it's order n, right?
N
It's
cross
just a
1.
dot product.
Oh yes, yes.
Yeah. Okay, and what about B?
So for B, so this is a vector and then multiplied by this thing and with another vector. So this will cost of the order of n square.
Right, because what you can do is you can first multiply C with R2 in order n square time,
Yes, yes,
and then C R2 is just a vector. So that vector you can multiply with R1 in order n time, right?
yes,
And A equals B just takes order one time. They are numbers. So the running time is order n square, right?
yes.
Okay. So now let's look at the success probability. Again, similar. If AB equals C, then the algorithm always outputs equal, right?
Yes.
The interesting case is when AB is not equals to C. So there is IG over here. Okay. So suppose that AB is not equals to C, then I'm calling D as AB and defining two vectors of variables, right? So here x1 to xn and y1 to yn are variables.
Mhm.
Then I'm defining two polynomials, P and Q. Okay, I messed up. So yeah, it's fine. I don't need IJ. Yeah. So I'm defining two polynomials. One is x transpose dy and another is x transpose cy. So
Yes,
what's the
yes.
degree of what's the degree of these two? Okay, let me define one more polynomial. Okay, so what's the degree of f?
So we would be having, I mean, all the variables in isolation, x1 and say log x.
Yes,
Everybody would be in
all the
isolation.
variables. So x1 to xn, huh?
So degree would be equals to 1 then.
2. Why? Because, okay, let's ignore this x transpose for y, for a y. Let's just look at dy. Dy is a vector, right?
Yes.
And every entry in dy is just a linear combination of y1 to yn.
Mhm, mhm, mhm. Yes.
So every entry of dy uh, has degree 1, right?
Yes.
Now every entry of x also has degree 1. And
Oh,
when I multi do this, the degree of x and degree of y add up, right?
yes, yes, yes.
Yeah, so this has degree 2. Similarly, this has degree 2. So the difference would have degree 2, right?
Yes, yes.
Okay. So now that we have defined this, here's the observation. Okay, okay, I don't need to write x1 to xn every time because I have defined them to be, yeah, I can just write x, right? Because x is this, y is this. Okay, so this is my claim. Now, why is this true?
So this is according to the definition. If p x comma y is not equals to the q of x comma y, then how can this p minus q be a zero quantity? Uh, unless we go for randomization kind of a thing.
No, no, no. Okay, so here this is the variable, this is the variable, everything is variable. Right? I have not done any randomization yet. My claim, okay, ignore this. My claim is that p and q are different polynomials. That's my claim.
Mhm.
So my question is, why is this claim true? Okay, so I've assumed that a, b, and c are different. So d and c are different, right?
Mhm.
So d is not equals to c. Therefore, there exists I comma j such that uh, okay, the ijth entry of d is not the same as the ijth entry of c, right?
Yes.
If two matrices are different, one of their entries must be different, right?
Mhm.
Now, px comma y is sum over I comma j xi ei yj. So I won't prove this, but do the usual matrix vector product, you would find out that this value is exactly this. Okay.
Mhm.
And similarly, q would be yeah. So Dij and Dij are different. So the coefficient of xi, yj are different in the polynomials, right? So the polynomials are different,
Yes. Yes.
right? And that implies that fx comma y is non-zero, right?
Mhm. Right.
Now, so what is A? R1I. Hmm. So is this fine? Because what was A? A was obtained by multiplying R1 to A and R2 to B. So we saw that A is this, right? R1 transpose AB R2, but this is and this is P of R1 comma R2. Is this fine?
Yes, yes,
Yeah. And similarly, B1 is Q of R1 comma R2.
yes, yes.
In fact, I didn't need to write this. I could have just written. Okay. And now I'm checking A equals B, right? So probability that and this is less than or equals to 2 over 4, which is 1 over 2. Okay, so are these steps fine? The first four?
Yes, and why did we take that set comprises of four elements only in the beginning of this proof?
I just wanted 1 over 2.
Okay,
The
okay.
degree was 2, right?
Yes, yes, yes.
Yeah, and I just wanted 1 over 2, so I took 4.
Yeah.
So is this fine?
Yes, yes, yes.
Yeah. And so over here the probability is like half. So let's say if you were to repeat this root n times, the probability would be 1 over 2 to the root n, right?
Yes.
So the total running time would be n to the 2.5, which is still better than, let's say, doing the naive matrix multiplication in the determinant algorithm, right?
Yes. But then
Yeah.
this algorithm only tests that whether the given matrix is same as the product of the two matrices or not. And
Yes.
probably we do not have algorithm to compute the product as such, right? In some
Yeah.
meta.
So yeah, i- if you had something, then the deterministic algorithm itself would work, right?
Yes.
Yeah. Yeah. So okay, before we end, so which type of algorithm is this?
Yeah, Monte Carlo.
Again, one-sided error, right?
Yeah.
Okay, so now I can just replace this by lecture 7. Yeah, so finally we are at the lecture boundary, but we have one lecture behind.
Yes, yes.
Yeah. So next time we would see some more applications of PIT. So we would see randomized uh, algorithm for checking if two matrices are similar, and then
Mhm.
an algorithm to like check if a bipartite graph has a perfect matching or
Yes.
yeah. So I think next week we would also be looking at like applications of PIT, and then we would move on to something else. Okay.
So I mean, till now I found this PIT pretty difficult, and maybe because of I don't understand that, maybe because of my mental blocks related to the handling of the polynomials or something else.
Okay.
Yeah, but then this PIT then seems to be more difficult to digest. But then the results are very interesting, and you explain
Yeah.
it so I mean with so much patience. Yeah, but the topic
Yeah.
as such is slightly difficult. Yeah.
Yeah. Okay. So for the next lecture, all you need to remember is the Schwarzschild lemma. That's it.
Okay, okay.
Yeah. So basically, what would happen in the next lecture is we would have some problem. Okay. So let's look at this Frival's algorithm, right? We had some problem. We somehow figured out a way to model it as a polynomial.
Yes, yes.
This is what happens in every algorithm using PI.
Okay, okay,
Using polynomials and apply Schwarzschild. That's it.
okay, okay.
Yeah. So the main part is how do you model it as a polynomial? For example, over here, the choice of P and Q mattered a lot, right?
Mhm. Right.
Yeah.
Yes.
It's just fine.
Yes, yes, absolutely fine. And will you
Yeah.
recommend
Okay.
some literature or something which I can, something simple which I can read, some book or something related to these topics?
For PMP, I think all of this, okay, most of this is present in that Aurora Bharat book. I think
Okay,
chapter 6 or 7 of the Aurora Bharat book, right?
okay, okay. I will refer that.
Yeah. Yeah. So I don't think Frival is present, but Schwarzschild lemma is present.
I could not hear you, but
Yeah.
can you share these notes?
So yeah, so I'll upload this week's video as well as this notes today itself.
Oh, thank you so very much.
Yeah, yeah.
Really,
Okay. Yeah.
thank you so
So
much.
then let's meet it. Yeah.
Thanks. Good night.
Okay. Let's meet next week. Bye.
Bye.
Oh, stop recording.